Hello everybody, my name is Hassan. In this video I would like to talk about something so remarkable in physics. Whenever I work with it, it always delights me. The topic I would like to talk about is dimensional analysis. What it is, why it is so useful, why it is ubiquitously used in physics. I'm going to talk about all these by also solving some examples to illustrate my points. So here's how it works. Assume that you have a physics problem and you want to predict a formula for this physics problem. And you write down the following. You have an equation on the left-hand side. You have the variable that you're interested in, which let's call x, is equal to some constant times variable 1 to the power a, variable 2 to the power b, and so on. In this equation, x is the variable that we are interested in. v1, v2, v3, and so on are the variables that we think this variable is most likely dependent on. C is a unitless constant. Now, with the formula written in this form, our job now is to find the exponents a, b, c, blah, blah. We will find those by writing the units of each variables and having one equation for each unit. I think it's going to be more clear if we solve an example. So here is the example. Consider a pendulum with a rope length of L, as I show in this figure, and a bob with a mass of M attached to the rope of length L. And we want to come up with a formula to predict period t of the oscillations. So let's apply this dimensional analysis. First of all, we list all the variables which we think this t might depend on. My guesses would be it might depend on L, it might depend on mass of the bob, it might depend on gravitational acceleration g, and it might also depend on theta, which is the release angle. The next thing that I need to do is to put down the units of these variables. The unit of the period is in time units. You can either write seconds here, you can write t, which denotes time. For L, the unit is length units, which is in meters, or you can just write capital L to denote length. The mass has the units of mass, and g, gravitational acceleration, has the units of length divided by time squared, and theta, we can call it as unitless. I can show by just a line here. The next thing we are going to do, we are going to write down this formula. T is the variable that we are interested. We're going to write t is equal to some constant, which is going to be a unitless constant, times the first variable, L, to the power a, second variable, m, to the power b, third variable, g, to the power c, and theta to the power d. Next thing, we are going to insert these units into this equation. T has the units of t, we can keep it as t, is identical to, c is unitless, we don't need to write it down. Length has the units of length, I just insert this one here, length to the power a. Mass has the units of m, capital M to the power b, times g has the units of length divided by time squared to the power c, and theta since it's unitless, we can absorb this in this constant term. So we can actually write down this is going to be a constant, but this constant might depend on theta. So this is the unitless part, and theta can be absorbed in this unitless part. The next thing we are going to do, we are going to equate the powers for each units. For t, for example, for time units, the power on the left-hand side is 1 because it's t to the 1. So on the left-hand side we have 1 is equal to, on the right-hand side, the only time component is this one, which is to the power minus 2c, because this is in the denominator, it's going to be minus. So it's minus 2c, minus 2c. There is no t here. There is no other t. So from here, we find that c should be minus 1 over 2. Another equation we can write is the equation for the length units. On the left-hand side, we don't have any L, which means we have L to the 0. So for L, let's write on the left-hand side, we have the power of 0 is equal to, on the right-hand side, if you look, it's this one and this one. So we have A plus C. And from this equation, since we know that C is minus 1 over 2, A is going to be plus 1 over 2, because it's minus C. We can write down another equation for mass. For mass units, on the left-hand side, we have m to 0. We don't have any mass, so it's 0 is equal to. We're only writing down the powers of these terms. We only have the mass here. So it's m to b. So I write down b here. There's no other m. So it's this one. So we have found A, B, and C for our proposed equation. If I insert these values and continue here, t is going to be equal to some constant, which might depend on theta, times L to 1 over 2, because A is 1 over 2, mass to B, m to 0, which is 1, so I don't need to write mass there, G to C, and C is minus 1 over 2, so G to minus 1 over 2, and theta we absorbed it in this constant C because it's unitless. Now we have this formula, and we have seen that this period has no mass dependency. That's something we obtained from only the dimensional analysis. And this formula I can simplify by writing this in square roots. So it's going to be square root of L divided by G. It's square root because these are half powers. G is in the denominator because it has negative power. So this is the formula for the period of the pendulum. This can be any constant. Let me give you the theoretical formula for this. If you delve into complexity of this problem, if you solve it using the mechanics, it's going to take a lot of time, but you're going to find the following formula. For small angles, for small theta, the formula for the period of the pendulum is 2 pi square root of L over G. It's exactly the same as in here. Okay? The dimensional analysis already told you that the period doesn't have any mass dependency, and the period increases proportional with the square root of L and decreases G, inversely proportional to the square root of G. So this is something fascinating. So you don't need to solve all these mechanical problems. The only thing that you do is equating the units on the left and right hand side of this equation. Now at this point, before I start solving another very interesting physics problem using dimensional analysis, I strongly recommend you to watch my pendulum experiment video, so you can check whether this formula is consistent with my experimental results in that video. Now, I would like to talk about the second example where dimensional analysis gives us a great insight. Here is the problem. We have a ball falling down due to gravity in a fluid which has a viscosity mu and a density rho, and we would like to calculate the drag force acting on this object. I start my dimensional analysis by listing all the variables which can have an effect on the drag force. So first I write down the drag force as F. And I think the size of the object might have anything to do with the drag force. So I write down D, which might be the diameter or the radius of the object. I think the viscosity or the density of the fluid can affect. And also, of course, the velocity of the object, I think, should affect. So these are the variables that I list, I think, that will affect the drag force. The next thing I do is I write down the units of each variables. The unit of force is equal to, since it's kilograms times meters per second square, it's mass times length divided by time square. The unit of the diameter or the size of the object is length, L, and the unit of the viscosity is mass divided by length times time, and the density of the fluid has the units of mass divided by volume, which is mass divided by length cube. I should note that I always try to use the elementary units like the mass, length, and time. Instead of the volume, I write it in the form of the length cube. For the velocity, the unit is, as you know, length divided by time, because it's meters per second. The next thing that I do is I write down the formula. I predict the following formula. Force is equal to some constant times my first variable, d to the power a. My second variable, viscosity to the power b. Third variable, density to the power c. And velocity to the power d. Now, I insert the units instead of the variables. Instead of F, I write down mass length divided by time square is equal to, I don't write the constant because it's unitless, it has no units. Instead of diameter, I write length to power A. Instead of viscosity, I write mass divided by length times time to the power B. Instead of density rho, I write down mass divided by length cube to the power C. Instead of velocity, I write down length divided by time to the power D. Next thing I need to do is I'm going to write down for each elementary units, for mass, for length, for time, I'm going to equate the powers on the left hand side and the right hand side. For the length, I have length to the power 1 on the left hand side, so it's 1 is equal to, on the right hand side I have this, and this. I have 3 length terms. So it's a minus 2b, because it's in the denominator, that's why it's minus. It's b, sorry, it's not 2b, it's b. Let me cancel this one. And minus 3c, because it's in the denominator, it's minus, and we have c, and we have the power of 3, so they're multiplied. And we also have, actually, I missed this one, we also have L to D, so we have plus D. This is our first equation. Second equation we can write for the mass. The power of the mass is 1 on the left hand side, because it's mass to the power 1, is equal to, we have two mass terms here, mass to the power b, mass to the power c plus c. We don't have any other mass. Okay, so far so good. Now we write down another equation for time. It's -2, because it's t to the power -2, is equal to, on the right hand side, we have two time terms. One is -b, the other is -d. Now, let's pause a little bit and think about this for a couple of seconds. I have three equations, but I have 1, 2, 3, 4 unknowns. So I have one extra unknown. So it's not possible for me to solve this equation. So should I just not use the dimensional analysis? No, I can use the dimensional analysis still. Here's what we do, which is going to give us more insight about the problem. When I put down the density rho and the viscosity mu, I had some suspicions about whether it's going to be the density or the viscosity which is going to affect the system. So there are two scenarios that I can choose. I can set the exponent b equal to 0, or I can set the exponent c equal to 0. Maybe none of the cases is true, but let's do two of the scenarios. Let's follow two of the scenarios. Let's set b is equal to 0 first. Scenario 1. B is equal to 0. If you set b is equal to 0, then you find from this equation, you find that c is equal to 1. From here, you find that d is equal to 2. And if you set c is equal to 1 and d is equal to 2, you're going to have 0 here. So this is -3 plus 2. This is -1. So a is going to be 2. This is scenario 1. And for this scenario, the drag force is going to be equal to some constant times e to the power 2. We don't have mu term. We have rho to the power c, which is 1, and v to the power d, which is v squared, because d is 2. This is the first scenario. So I can have this formula, or scenario 2. Let's take c is equal to 0 and omit the density term. If we take c is equal to 0, then b is equal to 1. And what else? If b is equal to 1, d is equal to also 1. And if b and d are 1, these cancel and c is 0, a is going to be 1. This is the second scenario, and for the second scenario, the force is going to be equal to some constant. Let's call this constant 2, and let's call this constant 1. Constant 2 times d to the power a, which is d to the power 1, mu to the power b, which is mu to the power 1, rho to the power 0, v to the power d, which is v to the power 1. So this is the formula for the second scenario. So we have come up with two possibilities. Either this is true or this is true, or you can say maybe none of these true. But here's the thing. I can even have a formula for f, which is going to be a linear combination of these two. I'm going to tell you the reason in a second. If I add these two terms, I'm going to have a formula for the force which is consistent in terms of the units, because the unit of the left hand side is the force units, and the unit of this first term is force units, and the limit of the second term is also newtons, which is force units. Which means that depending on the contribution of these two terms, this equation might still be true. You can take C10 and come up with only this formula. You can take C20 and come up with only this formula. Or you can put non-zero terms for C1 and C2, and you can find a linear combination of these two terms. Now, here's the thing. There is another thing that this formula tells us. It's the following. You can think about what is the contribution of this term as opposed to this term. So you can divide this term to find a unitless number, which is d squared rho v squared divided by d mu v. So depending on which one is larger, you're going to have an idea about whose contribution is going to be larger in this equation. If you make the algebra, one of the v's cancel, one of the d's cancel, and you come up with the following formula: rho v d divided by mu. This is dimensionless because this was in units of forces, this was in units of forces, so this should be unitless, and this unitless number has a name, and it's called the Raynald number. It's abbreviated as RE. Now, this dimensional analysis gave us some insight about this problem. Here's what it gave us. There's a dimensionless number, which is called a Raynald number, and it tells us that when it's very large, the contribution of this first term is large. Then that means you can take this formula. If this Raynald number is very low, very small, the contribution of this one is small, but the contribution of this one is very large, which means that you can take this formula as the drag force. So isn't this very interesting that this dimensional analysis gave us some insight about the problem, which gives us two different formulas in two different physical mediums? Thank you very much for watching me. If you would like to get notifications about my upcoming videos, please subscribe to my channel, and you can also hit the notification button to get notified about my upcoming videos. Thank you very much for watching me.